Okay, first of all, thank you to the organizer for bringing us to this wonderful place. Okay, the topic I want to talk about today is based on some thoughts we have had with my colleagues here over the last few years, and that this conference helped us in focus on finally writing up the paper that has been recently put in the archives. The plan of the talk is, well, what should we expect the program of the recovery of space-time, classical notions of space-time to achieve, how we visualize that program as divided into some steps. Then I will talk about what is the notion of effective geometry, how we think one can recover the notion of effective geometry at a given scale if one was given some other notion in another scale. That, in some sense, is going to tell us how to connect the different steps in the program. Then we will see some of the issues that appear in this program when we examine in detail one of the steps of this program, but our view is that similar problems will appear in each one of these steps. In particular, I will point out to an issue that was surprising to us, which is the failure of a certain type of associativity that we would expect the program to have, and apparently it doesn't. And then I will end up with some final comments. The talk was planned for a little bit longer time. I planned it before I was allocated the time, so it's going to be a little bit squeezed here. Okay, so fortunately some of the issues that I've been talking about have been already mentioned by other speakers. In particular, I want to rely on this functionalist, to a degree, on this functionalist point of view that was presented to us yesterday. And the basic idea is that without specifying what are the objects which you use to probe space-time, the space-time notion should be meaningless. In other words, when we say that the space-time separation between these two events is something, we should not be able to give a numerical value to it before we specify what kind of object we use to determine that space-like separation. In other words, if one thinks about it, it's clear that one cannot find any objective criteria to define what are the good clocks or the good rulers with which we use to explore space-time. And what we actually do in physics is to choose some particular convenient ones. There is a fact that there are particular choices of these rulers and clocks for which we obtain notions of laws of physics that are particularly simple. In other words, we may have used rubber bands as a ruler, or the wings, the flapping of the wings of a fly as a clock, but we will obtain notions of times and length that generate laws of physics that are extremely complex. And that's why we don't use it. We use certain type of atomic oscillations to define good times. We used to use platinum iridium bar to define length. Now we use light and say speed is 1. And then we use free particles, that is, particles that are free of electromagnetic weak and strong interactions, to determine what is an inertial frame. And then basically what one considers this issue of how do you obtain an inertial frame. You take two non-collinearly moving particles that are free. You adjust yourself to move in such a way that you see these two particles moving inertially, and then the law of inertia is simply the statement that all other particles, when viewed from that particular frame, also move inertially. With that kind of approach, the equivalence principle and the law of inertia are basically the same issue, and for us that is the important lesson of general relativity, the equating of these two notions. And of course, the question is, how should this equivalence principle and this identification be, what kind of role should that play in the program leading to the emergence of our notions of space-time? Our notion is that if actually GR is going to be recovered from some quantum gravity theory with this feature, this identification of the equivalence principle and the law of inertia appearing in a natural way, it's probably natural to assume that that identification should be, in some sense, built in at every level of the recovery program and not only at the last level. In other words, what I'm trying to say here is that if we find a method to start from a quantum gravity theory and describe the emergence of things like areas, volumes, four volumes, and things of that sort, it's not clear that the geometry that we would recover would be such that the objects, the point-like objects that eventually emerge from that theory would be following the geodesics of that space-time. And we want that thing to be built in the program to ensure that that's the case. Normally, one thinks that the recovery of classical space-time would be achieved starting from a quantum gravity theory from some type of averaging over a certain scale. But the question is, what is the meaning of, first of all, of such scale? We know that, an object suffers a Lorentz contraction when we change frames, so it's not easy to assign to it a scale unless we say, well, this object is at a certain, if in its rest frame or something like that. So we don't know what exactly are the scales over which we should be averaging. And moreover, we don't know what is this averaging procedure. These two issues, the fact that we have a problem in defining the averaging and the fact that we want objects, physical objects, to play their natural role in specifying what we mean by geometry, suggest that we put the two ideas together and offer an answer based on that. Use physical material objects to actually define the averaging and define also the geometry on which they seem to be, or the space-time in which they seem to be. Okay, so basically the idea is we all have this idea that at certain scales, space-time may look flat, but at the deeper scales, things may look extremely weird, and we would like to understand how, starting from a level of this sort, we would get to this kind of level. So the idea is to take a physical object that is in some sense large compared to this, see how this object moves, follow its evolution in time, assign to it a word line if you want, and decide that that word line is the geodesic of the space-time that you want to recover. That's the basic strategy. Okay, so how would this strategy be in principle implemented? Well, imagine, first of all, we have to recognize that we will have to pass through certain different regimes. First, we would start with the full quantum gravity regime, in which space-time is described in terms of very non-space-like notions, for instance, spin networks or things of that sort, causal sets, etc. And of course, since we nevertheless want matter degrees of freedom to be to live in the corresponding space-time, these matter degrees of freedom must appear as subsidiary degrees of freedom or mathematical objects that are tied to these objects that are described in the space-time. In other words, we may have to assign to the spin networks either to the vertices or the links themselves, some other quantum numbers that characterize the fact that there are fields living on this space-time. Sorry, I skipped it. Then from such a space-time, from such a regime, we would hopefully be able to go to the next regime, which we call the hard semi-classical regime, in which we already have some notions of space-time. But this initial regime, semi-classical regime, may be such that variations of curvature are very large over the regions of interest. The curvatures themselves may be small compared to the Planck scale, but they would vary widely, more or less like in the picture I showed before, over the regions over which the fundamental excitations of matter live. That is a very hard regime to talk about. Then we would pass eventually by some sort of averaging to a regime in which we have obtained some relatively smooth description of space-time. It's like the second slide that I showed, where you already have a description of space-time in which the curvatures are, the variations of the curvatures are small over relatively extended regions. The regions we are thinking of about are the regions over which these fundamental excitations of matter are dispersed. From there, we eventually would pass to something we call the hard classical regime, where we have a classical description of space-time and point-like particles. Moving along some specific word lines, and from there eventually we would be able to do some averaging and pass to a description, what we call the soft classical regime, where one has classical space-time and matter distributed by a smooth fluid that describes in some effective way a very large collection of particles. So this is something to have in mind. In going from each one of these regimes to the next one, we would have to do some averaging, and the idea is that the averaging should be performed in the fashion that I have just described. The regime number 5 is actually the regime for which GR was formulated. That is some fluid, energy momentum tensor, is a smooth field over the manifold. The regime 4 is one we trust the theory to be reliable, but it's a regime that has not really been explored to any substantial degree. In particular, we don't really have any test of GR in which the objects that source the gravitational field may be looked as point-like particles. All precision tests of GR we have involve extended objects like the probes in a torsion pendulum or the smooth spheres in gravity probe B, etc. Regime 3 is a regime of which we have some experimental empirical knowledge because that, if I remind you, is the regime in which we characterize matter in terms of quantum fields. That regime is, for instance, the regime in which we look at inflationary cosmology and the formation of the seeds of cosmic structure, and we have empirical data that supports the theory. Regime 2, the hard semi-classical regime, is something that has is empirically unexplored, and of course, needless to say that regime 1, full quantum gravity, is unexplored as well. Okay, so how would these connecting steps look like? Well, in the regime 1 and passing to regime 2, well, regime 1 is not completely under control, so we don't know how to do that. In particular, in regime 1, if quantum gravity is defined in a canonical, is constructed in some sort of canonical approach, we know we face the issue of time. Regime 2 is the semi-classical regime where we expect space-time to be described by a manifold with a metric, and in which fields are described in the language of quantum field theory in spacetime, and we expect something like this to hold. Here, this is a regime that mathematically at least is under control, except of course we need to deal with the issues of renormalization and specifying the counter terms. Regime 3 is also under control, but let's think for a moment about how we would go from regime 2 to regime 3. Presumably we will have energy momentum tensor, expectation value of the energy momentum tensor in that regime, would average it over certain regions of a suitable size to obtain some kind of smear energy momentum tensor, and then recover the metric, read from the behavior of this tensor the metric. What would that mean? Would mean finding an object, a tensor, which we call the effective metric of level 3, such that, for instance, this new average space energy momentum tensor is conserved. Of course, this is a very demanding program. We will not attempt anything like that here. What we will attempt is something much simpler. Let's look at regime 4, where we have a space-time, classical space-time filled with matter described in terms of the worldlines of particles. These particles, let's say, let them have mass mi, and the energy momentum tensor will be something like that, where these are the geodesics followed by each one of the particles. If we try to take this and go to if we try to obtain that regime 4 from regime 3, what we would have to do is take this expectation value of the energy momentum tensor of regime 3, identify the individual excitations. So by that I mean, imagine let's find the regions where the energy momentum tensor has support. So let's say this is the region where I find support for the energy momentum tensor, and I try to identify this as a particle, and try to assign to it a certain word line, and declare that to be the geodesics of the metric of the space-time that has emerged at that level. So I would like to find this tensor, that is the effective metric at this level of description, such that the word lines of these particles are geodesics, presumably by averaging this expectation value of the energy momentum tensor over these regions. Of course, to be able to read the metric at this point, it's not enough to have this geodesic. I would not need to be able to actually integrate the metric. I will need to crisscross the region of interest with other word lines and other energy momentum tensors, and decide that these two curves are geodesics of the metric, and from that try to read the metric, the underlying metric of the space. Here we have a problem in which I would like to say that the object that I have, with which I have tested the spacetime in this direction, is the same object with which I have tested the spacetime in this direction. And it's, however, not clear what that means. How do I define, what do I have to do to identify this object with this object? How do I say they are the same object? Okay, that will appear later on. Let me jump to this. Something similar goes in going from regime 4 to regime 5. So let me skip it for the sake of time. What we will attempt here is something much simpler. What we will concentrate in something very simple, which is regime 4, in which particles are described by word lines. Point particles are described by word lines, but I would like to change the scale over which I have done the average. So the idea would be that at this point I take now this thing that I have previously described as being the support of the expectation value of the energy momentum tensor and replace it by something much simpler with which is easier to work, which is a collection of lines of point particles, which I'm going to consider as an extended object. And then I'm going to try to assign to this extended object a center of mass word line. And to this center of mass word line, I will use to define what is the metric at that scale. And this I would do presumably for all regions of space-time with similar objects, and from there read what is this emergent effective metric at this new scale. Okay, so now let me go into the details of how this process is to be done. The idea is that similar processes should be used in all the schemes. Well, first of all, the problem here is dealing with the notion of center of mass in general relativity, which is a very subtle notion. In standard, in Newtonian mechanics, we have this formula here, it should be big cells. We have this standard formula for computing the center of mass. One, in passing to special relativity, we would like to generalize this notion, but this notion is problematic if we go to special relativity, in particular because there are particles with zero mass that nevertheless have momentum. Therefore, it's better to choose something like this, weight the position of the particles by the mass. But of course, something like this would produce a word line that depends on the inertial frame in which we started doing this. So this recipe as it stands here is not covariant. The covariant recipe devised by Price in the 60s is basically to first go to the rest frame of the collection of particles. So go to the frame in which the total momentum is the frame that is moving in the direction of the total momentum of the particle. So basically choose this 4 velocity, and in that frame, in that inertial frame, evaluate this center of mass and obtain the word line, and then define the center of mass word line in any other frame by simply the transformation of this word line. That of course is a covariant version. The problem now is to generalize that idea to general relativity. So here we follow Beiglb, which produced a recipe rather complicated, but which in some sense generalizes this notion. The idea first is that I need to define the rest frame of this collection of particles. Oh God. Okay, so how do I define the rest frame of the collection of particles? First, I take an arbitrary point. I assume that this is the rest frame of the collection of particles, construct the space-like hypersurface that is perpendicular to this one and is generated by geodesics that are perpendicular to this one. Look at the intersection of my word lines with my particles, take the momenta of these particles, parallel transport them to this point, and add them up, finding out the total momenta of this system as viewed from the point of view of an observer that moves in this 4 direction. That momenta will not in general be in the same direction as I'm moving, but then I look at this as a map from some 4 vectors to 4 vectors and look for the, normalize this vector, and then look for the fixed point of the map. That defines for me at each point the observer that sees this collection of particles at rest. In that, yeah.
Sorry, you said you parallel transport along which curve are you choosing?
Okay, so first I take my point, take a arbitrary 4 velocity, construct the hypersurface that is, construct the geodesics that are perpendicular to this direction, and construct the hypersurface here. And now I take the momenta here, so parallel transport along the geodesic on that hypersurface that connects this point to this point.
Okay. And so how much, you're assuming a lot of...
Yeah, we are assuming here we have a convex normal hole,
right.
So there is a unique geodesic connecting any points.
And a lot of these geometries already there, all these classical geometries.
Yeah. So what I'm saying is, the exercise I'm showing here is going from level 4 to level 4 prime. Our point of view, however, is that similar problems you will face in every step of the okay. But here things are easy, are manageable, so we can do that. Okay, so this way you produce a field that defines for you the rest frame at each point, the observer at each point that sees this collection of particles at rest. And now you're trying to look for the center of mass, and looking for the center of mass involves the following. Involves guessing that this point is on the center of mass, taking its for velocity, doing the same construction again, and looking for the correction to the center of mass word line. What is the correction of the center of mass word line? Basically, start from this point, compute what is the segment that connects our point to the position of the particle on this hypersurface, use the exponential map to assign a vector to that position. So you find the vector such that exponentiating that vector you get to the position of the particle on the hypersurface. And that assigns to every particle this quantity we call xi. And then we do the recipe of the center of mass. We do the recipe of the center of mass basically by summing up the position of the vector of these positions, summing up these positions of the particles I, weighted by the energies measuring that frame of those particles, and exponentiating back. So that would give us, in some sense, an average, a weighted average of the position of these particles, and this would be the correction of the center of mass if I assume that I started from this point. But of course, that recipe depends on which point I started, so it's not covariant so far. The idea, however, is that you should look for those points in which there is no correction for the center of mass. In other words, the points for which this map maps the point into itself, for which you need this recipe, this actual quantity to hold. And then the points that satisfy this recipe are points that are on the center of mass, word line, and Beiglb has shown that this recipe, in fact, generates a continuous time-like curve, which is generically not the geodesic of the underlying metric. However, we feel that this is the natural definition of the effective geodesic of the spacetime that you would obtain by probing it with objects of this size. I'm done. Okay. So this seems to be a reasonable recipe. The problem with this recipe is that first of all, the word lines that you obtain depend strongly on the type of object you use. Not only on the size of the object, but on things like the internal energy of the object that you use as a problem. So you would get very different geodesics generically depending on the objects you do. We have done explicit calculations of something very simple. This is what we call a hot object. So it's an object made out of free particles that used to define the center of mass word line. And with these objects, we generate lines, compute the deviation of these word lines as if they were geodesics, and compute from there, extract the resulting curvature using basically something like the Sudarsky equation. And we find that as the object's kinetic energy changes from 0 to some large value, the effective curvature that you measure of the space-time compared to the actual curvature of the space-time changes dramatically. Something similar happens when the object you use to probe the space-time is extended. Here is represented, the extended object is represented by simply 2 point-like particles that define an effective object that is moving along this center of mass word line. With those kinds of objects, we again do the similar analysis, and we find that that, again, the curvature of the underlying spacetime that you obtain is the changes with the size of the object. Of course, in the limit in which you go to zero, you recover the actual curvature. The idea that we want to convey here is that, of course, the limit in which the size of the object goes to zero makes no sense in the quantum realm. So you cannot actually hope to take the limit. You will have to deal with objects that have an extended size. But even more worrisome is the fact that if you start with a collection of worldline of particles and you group them in different ways, I start with two particles here and a third particle. I group these two particles to produce the effective object AB. And with this object, I combine them to produce the effective object ABC. I obtain different results than if I combine them the three together. So the recipe is not even associative, which is a very serious problem. How are you going to apply this recipe? So our point is that since we are facing this very serious type of issues appearing in the regime in which we presumably have a lot of control, very similar or even worse kind of problems are going to appear in going from every regime to every other one. So that's the crux of the story. Let me finish because I have exceeded my time by several minutes already. So thank you very much.
Thank you very much. Let's now hear Sudarsky from Geneva-University. Please try to be short and to give a short answer so we have more time for the...
Yeah, so could you, if you can go to the slide where you talked about the different regimes, I just have first a clarification.
Yep.
What is the difference between regime 2 and regime 3? Because if you just go to the definitions of the different regimes.
Right. Regime 2, we imagine the regime in which you are trying to consider an object of this extension, and within the object, space-time varies rapidly. So that's a regime in which, for instance, in this graph, in this picture that I have, you are trying to probe space-time with an object of this size.
Right.
That is a hard semi-classical regime. And on the other hand, you could try to probe space-time with something of this size. Then you would be in regime number 3, because over this region, the space-time is, but the variations of the curvature are very small.
Okay, so in that case, what is the difference between regime 3 and regime 4?
Oh, regime 4 is already classical. The regime 4 is the classical regime where you describe particles in terms of point-like objects moving on a given geometry.
So regime 3 and regime 4 is only the difference is in the matter side? Because on the background...
Regime 3, the change from 3 to 4 is in going from semi-classical, so matter is described quantum mechanically here. Here, matter is described already classical.
So only on the matter side, right?
Right.
Okay.
Yeah, we left the full quantum regime unexplored. From our point of view, we are very agnostic about what is the quantum gravity theory. The only point we make about this quantum gravity regime is that it should have the property that the matter degrees of freedom are embedded or are attached to the space-time degrees of freedom to realize the notion that matter lives in space-time.
Okay,
That's
so let me just end with one comment on the question, which is,
yep.
I very much like this idea that one should worry about how matter couples to gravity if one wants to think about quantum gravity. This is very much worried in approaches like string theory, but not so much in other approaches. That's very nice. But but you seem to still hold on to some properties of matter like center of mass, coordinates, and so on. But couldn't one, if you are going to be radical about the space-time picture and say that this is emergent, couldn't one think that in regime 3 particularly, you have some notions of expectation values of your stress energy tensor like you were doing, yeah. but not any corresponding definitions for center of mass?
No, I agree 100%. This is the object we would have. We would have an energy momentum tensor expectation value. But then, my question is, how do you go from that regime to regime 4? Then presumably, you want to take this region over which you have the expectation value of the energy momentum tensor being non-vanishing, and say, that somehow is a particle for me. And now you want to convert that into a word line. The only idea that seems natural is, people can invent other ideas, but the most natural thing would be a covariant notion of center of mass, which fortunately exists. So we think that that would be the process. And then once you have this world line, you say, okay, if these are the world lines of these free particles, what is the space-time? What is the metric?
Yeah, just the point is, shouldn't it depend more on the states you choose to do this averaging of the stress energy tensor? I don't see where that information is going in.
Oh no, of course. What you imagine is that you have a regime in which you have space-time and a quantum field theory in a given state. So in that given state, there will be an expectation value of the energy momentum tensor. And for that given state, you would say, well, this state corresponds to particles moving in these different ways.
But what are the properties of the states?
No, well, you use the particular state you want to study. So,
right.
So somebody tells you, well, here I have a quantum gravity or a semi-classical description of the universe. So, and here is the state of the universe. And you say, okay, how does that look if I want to describe it classically? So they were given, these things were given to you in regime 3. Both the space-time was given to you and the state of the matter fields were given to you. And now you are supposed to read from that what is the description at the other level. That is the recipe, the process we have in mind.
Okay, let's talk later. Thank you.
Thank you. Question? Lucio?
This may be a very basic question, but I mean, so you couple the gravitational, or the gravitational field is sourced by the expectation value of the energy momentum tensor. Right. But in general, that energy momentum tensor can have widely spaced superpositions of matter distributions.
Yeah.
And so I'm wondering, in order, I mean, I guess intuitively it would seem more natural to couple the gravitational field to some, say, branch relative expectation value of the energy momentum tensor, relative to which, right, the energy momentum tensor is localized. Right. So on a particular branch, right, that's really where you get the classicality or the localized matter distribution. If you want to recover, right, the classical kind of source equations, right, it would seem that really in order to recover classicality, you don't want to couple to the full expectation value, but just to the expectation value of the energy momentum tensor on a particular branch.
I agree with you that certain quantum states would produce things that are not susceptible to a classical description. So the regime in which we're talking about, in which you have a huge superposition of energy momentum tensor here with nothing there and the opposite, that is a regime which I would say is not suitable for a classical description. This idea that I would decompose it in branches, well, then you're doing something else, right? But at the end, you're going to stay with one branch in which one, if that's your preference, take branches, in which you have one state that is more or less localized, and from that you will try to read that. I agree that that's a way to go from something very non-classical to something more classical. I don't know if this is the correct way, if that correctly describes nature. But my point is that even if you do that, even if you concentrate only on those states that are semi-classical in that sense, that don't involve huge superpositions, you have still an issue of how I read this, the geometry that underlies the motion of that, and that has this point. But I agree with you, there will be regimes in which the semi-classical description will not be particularly useful.
Thanks.
Thank you. Towards the end where you were pointed, I think you were sort of pointing to how looking at the trajectories of the center of mass would not return the curvature of the underlying space-time, if I get that right. But the bodies you were using had pretty low n. They were pretty simple.
Yeah.
So my question is that, if you're thinking of actual test bodies, they're probably very large n. And so are those deviations a function? How do they go with the number of particles of which these bodies are?
Well, actual calculations we have only done with 2 or 3 particles. These calculations are extremely hard. Yeah. So actually, performing it, so we took very simple space-times, basically the Sitter space-time, put very simple number of particles. These issues arise. Maybe they will be averaged out if I choose things in a very convenient way, but they are not always going to be averaged out. And in particular, I think this issue of non-associativity is going to remain there as a very serious impediment for the program. So things could be better, but we already at this level of simplicity we find very bad features.
Okay, so you think even if you take the large n, the associativity or the non-associativity is going to remain?
Look, the non-associativity is not infinite. The non-associativity actually, I have written here an expression for more or less how the non-associativity goes. I wrote a schematic expression because the actual expression is much more complicated. But it basically goes, the non-associativity, this quantity that measures the difference of the position of the center of mass when you combine AB first and then with C or ABC or something like that, is an expression that involves the relative positions of the particles, the curvature tensor, so when curvature is 0, you don't get this problem. In flat space-time there is no problem. The total spin of the system, the total momentum of the system, and the energy of the system. So in regions where curvature is small compared to the size of the things, the thing is not so bad. Of course, we worry very much if you are in something like regime 2, the hard classical regime, which I remind you is the regime in which I want to average. If I want to take this region, average over a region of this size, where curvatures are varying widely, then I expect a very high level of non-associativity to occur. It's going to be much less problematic when I try to average something over something like this.
So, but to get this right, the particular case you were doing was actually the R4 to R4 prime case, right? So that is a regime maybe where the curvature is varying slowly with compared to the size.
That's where we could compute things, right?
So does that maybe so maybe that's not the right thing to do in the lower levels of the
in the lower level,
like
in the more profound level.
Yeah.
Well, we haven't done any calculation in this space-time. It's very worrisome that we are obtaining this kind of result. If these results extrapolate in some way to this regime, it's going to be very bad. It could well be, it may well be that we happen to be very lucky and this doesn't happen. I don't see that really.
So it's kind of a sign that maybe the geometric notions are breaking down at a higher level than one would have thought. That one won't be able to reconstruct something like, the ability to reconstruct curvature in this way will fail.
We're finding that as a serious problem, in a regime where things should be under control and things are, more the most mild we could imagine. We expect things to get worse here, but that is just an expectation. Yeah.
Thank you.
Okay, we have time for one or two last questions.
Yes, regarding your R1 level, so the most fundamental one, you are saying that basically matter degrees of freedom are to be characterized as subsidiary mathematical objects that are attached to the fundamental pre-geometrical degrees of freedom.
Yeah.
Now, I would like to know a little bit more about that because that seems a little bit generic. If that means that every fundamental theory has to recover at a certain level this picture of matter living in space-time, then every empirically adequate fundamental theory will, let's say, fulfill your requirement. That will be trivial. Otherwise, I would like to understand this attachment requirement because you can have an example, for example, I don't know, there's this theory by Bilson-Thompson where at the fundamental level you have just topological degrees of freedom. So basically you can represent the state of affairs as a very complicated graph where the edges form ribbons and stuff like that. then of course there are some, let's say, function that send those ribbons to some material degree of freedom at a certain classical level. Would that be enough for you to say?
So I don't know this. I don't know this theories and various of the proposals of quantum theories of quantum gravity. I'm only familiar with. In loop quantum gravity, people think that way, that you would assign spinors degrees of freedom or gauge degrees of freedom to either the vertices or the links. In causal set theory, for instance, people assign to the points that make up the causal set values of a scalar quantity if they want to talk about the quantum field in there. If you have a theory in which matter is over there, completely unconnected with space-time, I don't know how you make sense of the theory, because I cannot think of matter living outside of space-time, perhaps some of them I can. But normally you attach them to say, well, in this, eventually you want to say, in this region of space-time there is matter, and in this region there is none, or something of that sort. If your theory doesn't have any linkage of where things are, I really don't know what kind of space-time are we talking